You can add, subtract, multiply all day and still be stuck. The problem is altitude, not effort. So when patches multiply and exceptions crowd the page, the work is telling you look from higher up. And today we'll move from arithmetic to algebra. So that means new rules, new operations, and symbols that scale understanding. Everyone who has learned math remembers a moment when the old way of doing things suddenly felt too small. You can still add, subtract, multiply, and divide. The small tool still worked, but the problems grew larger and the methods more awkward. And then, almost overnight, another language made everything simpler. That leap is the emergence of a higher viewpoint. And today, I want to make that emergence concrete by using Lonergan's pilot case. So that's the move from arithmetic to elementary algebra. And we'll see why some problems require a higher viewpoint, how to recognize that you actually need it, how to formulate it, why symbolism is a decisive aid to insight, and it's not just a decoration. So let's begin where Lonergan begins, with positive integers. So 1, 2, 3, 4, etc., etc. A child learns 1 plus 1 is 2 and 2 plus 1 is 3 and compare it that pattern. But the real power lies in the and so on. So it's that etc., etc., etc. And you have to take that not as a filter. Those are actual signals for an insight. You understand the series only if you grasp how the defining move continues indefinitely. Without that grasp, no teacherly patience can conjure and communicate the meaning of etc. The insight is that engine. It's what makes the infinite series of etc. intelligible. From there, you construct addition tables. You say, when equals are added to equals, the results are equal. And then you generate a table for adding 2, then 3, then 4, each by a simple rule applied again and again and again. The results bloom into an indefinitely great expansion, what Lonergan calls a homogeneous expansion. And that's driven not exactly by memorizing entry level, but by catching on to the rule that produces them. Insight grounds those tables. The tables display the reach of the insight itself. So up to this point, the image of merely doing arithmetic may feel sufficient. So, writing down similar digits, arranging columns, carrying, borrowing, filling in entries of tables. You could, at least in principle, recreate from a few basic postulates, but eventually a limit approaches. The repertoire swells, fractions, negatives, roots, and the old rules begin to feel lopsided and piecemeal. You can still push through, but it's a push rather than a flow. And that felt resistance is a sign you need a higher viewpoint. Lonergan names the shift directly and gives it a simple structure. Distinguish rules, operations, and numbers. Define operations by rules. Define numbers, or more generally symbols, by the operations. Then find the rules that fix the operations that fix the numbers. The trick, as he calls it, is an insight that arises while you're still doing the old operations that expresses itself by formulating new rules. Under these new rules, the familiar acts of adding, multiplying, dividing, taking powers and roots, solving equations, each is refined, it's generalized, and it's made more symmetrical. The center of mass shifts. Numbers are now generated not merely by adding, but by any of the operations as newly and more exactly defined. That is the higher viewpoint. And notice how the old image gives way to the new. The initial world was a large, dynamic, virtual image of doing arithmetic. You could picture columns of figures, carries and borrows, handwritten tables, the whole busy work of grade school calculation. Now a different image organizes your effort, doing algebra. The alphabet enters, signs become rules, equations become the stage on which operations play out. The new rules are more exact, they're more general, they're more symmetrical, just as a perfectly defined circle is to a cartwheel sketch. The point, do not confuse it, is not that arithmetic was wrong. No, it was right at its level. The point is that the algebraic view sees further by seeing from higher up. If you made that transition, you already know something about all such transitions as such. Lonergan insists that mathematics grows through a series of these lifts. You do not jump from the positive integers to group theory in one bound. You walk a staircase of insights. Each step has its own rules, operations, and numbers or symbols. Each step also contains the virtual image within which the next step's rules can be grasped. The student who climbs that escalator becomes technically competent. And they don't become so by memorizing definitions, but by repeatedly performing the same kind of leap from one viewpoint to a higher one. Now, why does symbolism matter so much in this ascent? It's because it supplies the image that intelligence works on. Some symbols are far more fruitful than others. You can take the square root of 1764 easily. Try making that square root of the Roman numeral and feel how that symbol fights you. The difference is not arbitrary preference. No, don't confuse it with that. It's the apt symbols that display imminent patterns and invite operations whose dynamic fits the rules insight has grasped. For example, this from Leibniz guides the mind along certain theorems of the calculus. Newton's notion, elegant for its own purposes. It simply does not suggest as much of the structure simply by glancing at it. Apt symbolism runs in parallel with the higher viewpoint that you're about to formulate. So let's try to weave the strands. A child's etc. becomes a law-like expansion. A law-like expansion pressed by a new cases. And that yields what? Awkwardness. Awkwardness provokes a question for intelligence. Could a more general, more symmetrical set of rules reorganize the whole field? An insight occurs. You express it by formulating new rules. Those rules define operations. Those operations now generate the numbers, or better, the symbols of the next level. And as you work under those rules, you become capable of grasping a still higher set. This is development by higher viewpoints. And that pattern is not unique to mathematics. In empirical science, Lonergan makes a parallel point. The canon of operations, the demand to experiment, measure, correct, systematize, etc., drives inquiry upward. You begin with simple laws in ideal cases, discover their shortfalls in concrete circumstances, add further laws, and then need to understand the relations of many laws together. At a certain threshold, minor corrections aren't satisfactory. They don't suffice. A more radical transformation of concepts and postulates is demanded. That transformation is, again, a higher viewpoint. But because our pilot case is arithmetic into algebra, I think it merits that we deepen that one. So under the arithmetic viewpoint, numbers are what can be generated by repeated addition, structured by addition tables that themselves can be constructed by a single postulate, that is, add equals to equals and equals result. Under this viewpoint, negatives and fractions are foreign bodies you accommodate with patches, rules for signs, rules for fractions, special handling for division by zero, and so on. The patches make the old coat wearable, but they also reveal you are wearing a coat probably 2 sizes too small. So that means that algebra, and don't confuse this, it doesn't abolish the old operations. No, instead, it redefines them more generally. Number loosens into symbol. The alphabet X, Y, Z appears as the native inhabitants of the new land and not as the placeholders to be eliminated as quickly as possible. So I think that if we understand that, then we can see how a formula is a rule that covers a range of cases rather than a sentence about a single computation. This perspective change is striking. In arithmetic, you aimed to compute, but in algebra, you aim to express the structure of computations so that a single expression governs many instances. And that shift is what Lonergan means by a higher viewpoint, a new set of rules that generates and orders an even wider field. But there's potential objections. One could say something like, isn't a higher viewpoint just a fancy name for abstraction? Yeah, I think there's overlap, but Lonergan's point is more dynamic and more genetic. The higher viewpoint is discovered while operating at the lower level. It's not imposed from above, but emerges from within the virtual image of doing arithmetic, doing algebra, doing calculus. The mathematics teacher who can lead students through the emergence is guiding the act of understanding itself rather than merely teaching facts to be memorized. Consider, like, for example, the practical difference between rules. So in early algebra, you encounter rules for signs, for fractions, for equations, for indices. Their cumulative effect is to redefine addition, multiplication, powers, subtraction, division, roots. And under the new definition, every operation can yield a number. Now, broadly, that's a symbol, and any number can be the result of some operation. The field is closed under the operations as newly understood. And so the work can proceed without constant exceptions. And that closure is a hallmark of a genuine higher viewpoint. So I think that once you appreciate the dynamic, you can watch it reoccur. Let's take the example of moving from algebra to calculus. Limits and derivatives reorganize what rate and area mean. How about calculus to linear algebra? Vectors and matrices reorganize equations into transformations across spaces, and linear algebra to abstract algebra sees groups, rings, and fields reorganize operations by their axioms rather than their numerical content. And each time, symbols are chosen to be apt. They exhibit patterns, they cooperate with operations, they suggest theorems. Each time, the student is asked to catch on to the rules that will now generate the domain. That catching on is the insight that defines the higher viewpoint. So what then are the signs you need to climb? First, when patchwork multiplies, take for instance the special cases, exception handling, ad hoc fixes, the system is signaling that its rules are no longer symmetrical enough to carry the weight. Second, when new kinds of objects keep arriving, think of negatives, rationals, irrationals, complex numbers, vectors, functions, all of which must be taped onto the old wall. You likely need to rebuild the frame. And third, when your image is doing the subject no longer helps you anticipate the results, a new symbolic system may be needed to restore that anticipatory power. Now, none of this denies the value of the older viewpoint. No. In fact, the higher preserves and perfects the lower by sublating it, keeping the achievements, correcting the limits, and opening a larger horizon. Don't that become discarded by algebra? No, no, no. Instead, it's taken up, it's re-expressed, it's extended. And that's why a higher viewpoint isn't merely a bigger drawer of tricks, but an actual deeper grasp of what you are already doing. And Lonergan emphasizes how pedagogy should follow this inner logic. Students cannot leap from first principles to the most abstract frameworks. They must rehearse the same kind of transition repeatedly, each time within a virtual image rich enough to invite the next insight. A good course doesn't pile on topic after topic after topic. It sets the stage for the emergence of rules that reorganizes the field. And this is true in mathematics as it is in the laboratory, where the canon of operations keeps widening the field of relevant data until the old hypothesis must be rethought in a higher key. Now, I think that it merits me dedicating a word to the feel of symbolism from inside the work. When symbols are apt, they become a kind of tactile surface for the mind. They fit the hand. You can manipulate expressions in ways that mirror the rules you grasp, and the manipulations themselves prompt further insights. And this is why, historically, certain notations decisively accelerated discovery. What they did was they suggested operations and exposed invariants rather than simply record results. The better the fit between symbol and rule, the more smoothly the higher viewpoint can be inhabited. But what happens if you refuse the climb? In mathematics, you can get stuck multiplying exceptions. In science, you can get an accumulation of laws that you simply cannot combine. And you will be tempted to treat them as a mere congeries rather than a system. And Lonergan warns that the real work forces the ascent. To operate in concrete situations, you must know how many laws hang together, which presupposes which and where the boundaries of each lie. The pressures to systematize, felt in the need to use several laws at once, is exactly what drives higher viewpoints. Let me bring that theme back to the person. The whole arc from arithmetic to algebra, from lower to higher, maps the structure of intelligent development itself. We begin with images and simple rules. Through repeated acts of understanding, we reach more general frames within which many cases can be handled by a few principles. Insights accumulate into viewpoints, and lower viewpoints yield to higher viewpoints. The growth is the way intelligence meets larger and more complex fields of data. So don't confuse this with a mere luxury add-on. Now, two cautions complete the picture. First, a higher viewpoint is not automatically obvious. No, it requires a precise question and a prepared imagination, what Lonergan elsewhere calls the pure desire to know, focused on the relevant data. Second, the higher viewpoint is never the last word. As domains widen, invariants deepen, and the process repeats. The staircase keeps going. The humility appropriate to any working scientist or mathematician is to climb well, teach others how to climb, and expect that there's further stairs ahead. So here is a compact definition for your own use. A higher viewpoint is an insight that reorganizes a field by formulating new rules that define new operations, that generate and order new symbols, and as a consequence, they sublate the earlier viewpoints and extend their reach. It's discovered while working under the old rules. It becomes fully itself when expressed as the new rules. When you can state those rules and when the new symbols run smoothly under them, you've arrived. If you want to test for whether your symbol is apt, ask three questions. Does it reduce friction in routine manipulations? Does it display invariants that your rules say should be there? Does it suggest further theorems by the very way you write expressions? If yes to these, your symbols are cooperating with your viewpoint. If not, your notation may be pulling against your own intelligence. And I think Lonergan's counsel is really clear here when he says that symbolism should be chosen for the insights it enables. Finally, I think we need to recognize the pattern beyond mathematics in any disciplined field. A time comes when more facts, more patches, and more effort cannot replace a change of frame. At that threshold, the invitation is not to abandon rigor, but to climb to the form of rigor that can organize what the lower frame could only accumulate. The energy, the inertia of genuine learning is precisely this movement from below to above again and again and again. Higher viewpoints are how understanding scales. And that's the story for today. Why the arithmetic toolbox eventually feels too small, how algebra emerges as a higher viewpoint with new rules, operations, and symbols, why symbolism is decisive for grasping and using the new frame, and how this patterned ascent repeats across mathematics and science. Take it as a lens for your own work. When the patches multiply, when the exceptions crowd the page, consider whether you are being asked to see from above. And if so, ask for the rules that would make the operation sing as the symbols fall into place. Then write them down. You will have named your higher viewpoint. Now, before we wrap, in the next episode, which is episode 4, we'll learn to spot questions that require denying unexpected intelligibility and why that redirect saves time and error. So if this video helped, like the video, subscribe, turn on the notifications bell to stay updated.